Go Language Programming, Chapter 9, Unit 1. In this unit, we will cover Big O notation complexity, common algorithms orders by rate of growth, categorizing time complexity into classes. So the most important part of measuring efficiency is runtime analysis of your code or algorithms used in your program. The most commonly used form of measuring efficiency is called Big O analysis. So, that's how the efficiency is measured, by using a Big O notation. This method provides a concrete means of comparing two algorithms. So the formal definition of Big O analysis is quite mathematical, and basically it goes into quite a bit detail about understanding of the discrete math and linear algebra, so forth. But we don't need to, go into that much detail about understanding the Big O, because in this chapter, I will give you the real life examples that will make the Big O analysis understanding much more easy. So Big O analysis deals specifically with the time an algorithm takes to run as a function of the size of the input. So basically, when your algorithm is running, it all really depends upon what is the size of the input that you're going to provide. And based on the size, the algorithm's efficiency may change. So that's the key part of finding what would be the worst case that the amount of input that you give to your algorithm that will start going or degrading its performance. Okay, so basically a Big O notation for measuring the complexity of, so that's what the idea behind the Big O is, a notation for measuring the complexity of an algorithm. So we want to know it's how well it is going to perform, your algorithm, the code that you have written. So now basically algorithm is nothing but it's a step-by-step instructions that you write, your logic in your code, telling a program to execute in a certain way to solve a particular problem. So whenever you are writing a code, you are actually writing a code for the purpose of solving some problem. And it, depending upon how well you write your algorithm, the performance of your program will depend upon that. Okay, so basically the Big O specifically describes the worst case of an algorithm. So if you have written some code and you would want to find out that what would be its worst case, that would, that your code or your program will have to suffer the performance. So basically, that's the key part of finding it, the worst case of the code that you have written, so then you can improve on it. So uh, the worst case might be at a point where you have a really huge amount of input that you are giving to your algorithm. And when you give a very huge amount of input, then your algorithm might be suffering from that big input, and the performance of your algorithm will degrade based on because of the input that you're given. you know so that's what big O is all about, to find the worst case scenarios, and then based on that you can improve on it. So when analyzing algorithms or operations, we often consider the worst case scenario. Okay, so basically, for example, let's say um, you are searching for your car key in your study room, but you cannot find it. You searched all six drawers of your study table one at a time. Eventually, you found your car key hidden under your, let's say, Go language book in the last drawer of the study table. So in a big O notation, it would be a linear time, and it is represented with um, basically uh, in writing like this. So linear time is represented like this, like a big O n. Okay, so this is the worst case because you had to go through all six drawers in order to find the car key. Now, to have some different scenario, let's look at what will be the best case. Okay, so in the best case, you are looking for a car key in your study room, and you know where it's supposed to be, in your first drawer of your study table, and you found it right away. Okay, so in that case, the big O is basically suggests that it is a constant time, and you can just do big O like this, represented with the one. So that means you are you found it right away, so it's in a constant time. There is no performance degradation. You knew where your car keys are, and you got it right away. So in general, the big O notation will always assume the upper limit. So basically, upper limit is the one which gives you the worst case, okay, scenario, where the algorithm will perform the maximum number of iterations. So in the upper limit, when you give, and in when it is doing the maximum iteration, that would be the time where the worst case could happen. Okay, so uh, that's um, that's how you analyze the your algorithms. So the big O analysis is used for measuring the efficiency of algorithm based on time it takes for algorithm to run as a function of input. So now, as we were, as I was giving you the example initially, the linear time. So in that case, it because you had to go through every drawer of your study table just to find the keys. That means it was a time consuming, and the more the places that you would have to look, it would take more amount of time. So the input size. So if you have a study table with 100 drawers, then you might have to go through 100 drawers, for example. And that would be the worst case scenario. So the big O function is a mathematical term that gives a rough estimate of how speed of algorithm changes with the size of the input. So as you can see that if your size of the input is small, definitely the performance is not going to be as bad. But if your size of input is bigger, then the your uh, algorithm could change drastically. Okay, so that's the key part to when you are doing the uh, big O analysis for your algorithm. You need to first make sure how the effect of the amount of data would affect your algorithm. So the big O notation describes the complexity of source code using algebraic term. So initially, basically, to arrive at the big O notation, lots of algebraic functions were introduced and used, which I'm not going to cover in algebra or linear algebra in this chapter, but this big O notation really came from the algebraic equations that give the answers for to um, how to measure some some um, uh, deficiencies or worst cases in your algorithms. So the big O notation is a method for determining how fast or how slow algorithm is. So if you use big O notation to analyze your code, you could easily be able to determine how well your code is. Is it performing as it's supposed to? Based on how you use the big O notations to calculate how well your code is running. So it describes the execution time required or space. So big O notation, has these two things basically. Time it required, which we went over in the example just now about looking for the car keys, and so more the data, it will require more the time, and then the space meaning how much your in terms of a computer, how much memory it is going to be using, and that could also make the big O, or that could make your if your code algorithm is using more the memory or the disk space, the performance could become worse. So that's the two things that you have to basically understand when you are measuring the amount of code amount using the big O to know how well your code is performing. So now let's look at common algorithms by rate of growth. So we know, as we just discussed, the big O notation measures the worst case. You know, that's the key part of understanding the big O notation to find out the worst case of your algorithm. But we need to know just how poorly our algorithm will perform, so we evaluate by using one or all of the following big O algorithms. So you can, so these are different complexities of the way that you can measure your code. And in this case, it will tell you how well your algorithm will perform. So big O of 1, that is a constant time, so that will be the fastest one. Like the example that I was giving it to you, you know where your car keys are, and you just go and grab it, and that's it. Exact location, and and you found it right there. And then logarithmic. So basically, when you have a logarithmic behavior in your code, then it will be a little bit slower. Okay, it won't be in the constant time. And then if you have a linear time that is big O of n, that means it will be a little bit more slower, but you still are in a pretty good decent range. So linear is not that bad either if your code have this performance. It is still would be able to have you know good amount of response time. And also remember, nobody can really write every time the code which is in a constant time performance, because it's just not possible. Okay, so these algorithms, one of these algorithms, everybody has it in their code. Some of them might be very slow, some of them so if it is very very slow, then that's the key part. It's the worst case, so you need to have a way to improve on it. And then you have a log linear, that means we go of n times log n. Okay, so in that case, this becomes a little bit slower as well. So as you go down the list, it becomes more slower and slower. So big O of n square is a quadratic. Okay, so that is also not bad, but the worst will be n factorial. This, if you have it in your code, something like this, you should really try to find a way to at least come up till this or this algorithm. Okay, so you find the worst case, and then you try to improve on your algorithm, and to get the proper performance. So let's look at the categories, categorizing the time complexity into classes. Now, these are, big O, all these are just now that we went over, they all are basically a classes of big O notation. So in this following big O algorithm that, I will, these are the one that I'm covering in this chapter 9. And hopefully, by giving some real life big kind of examples and different scenarios, the things will become a little bit easier to understand. Okay, so we'll go over the constant time, which is big O of 1, that is instant delivery, that means direct approach. The code always need the same time, no matter how large the input set is, so basically, uh, it's just like the example that I was giving to you earlier when we started this unit. And in that case, you knew exactly where the which drawer that your car keys are, and you got it in a constant time right away. So, example would be accessing a single element in an array of n items in is an big O of 1 operation. So you want to get some number out of the array, and that's it. You found it right away, and that would be considered as a big O of 1. The linear time, which is big O of n, one at a time. So in that case, you go one element of the array, and then you go to the next element, and then the next element, and next element. So time needed for processing n elements grows linearly. So as you walk through the array, it will take time. So basically, the processing of n elements grows linearly. So one at a time. So it will go bigger. So example is iterating over an array, reading a file from start to end. So both of example, either iterating one element, each element of an array at a time, or reading a file from start to finish or end. Okay, so that will be the example of a linear time. Quadratic time, which is the complexity grows in quadratic time. So loop executes a total of n times n. Okay, so basically that would be n square. And complexity is big O of n times m, which is equals to n square. So example would be a nested for loop. Okay, so if you have in your code a nested for loop, then that means it will perform as a quadratic time. Okay, uh, so for each time the outer loop executes, the inner loop execute n times. Okay, so basically, that many times the inner loop has to go through each time the outer loop goes through one. So so that's how you can find out the complexity of your code. So big O of log n, or logarithmic time. The more data, the better. Okay, so in that case, the time the code needs to process n elements raises much slower than n for large values of n. So example would be a binary search on a sorted array, or locking up people, or looking up, not locking, looking up people in a phone book. So basically, what do you do if you are looking for somebody in the phone book? You know the name, and of course you're looking for the phone number. So basically, and the phone book is already organized alphabetically, so you just go to those alphabetized pages and look. So 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 how to divide the phone books in different alphabetized characters. So the phone book is already divided, so you know under which alphabet the name that you're looking for is going to be found. Okay, so if you are doing the binary search, for example, for the sorted array, then in that case, you will go and make the array half every time, and look in that portion of the array for that number that you are looking for. So that's how the all of these big O notations can be used for within your code that you write to find the worst case scenarios and then improve on them. Okay, so basically that concludes this this unit.